This is a video walkthrough for practice 12.2 on infinite discontinuities. In 1 through 6, we're asked to write the functions in fully simplified form with a stated domain if needed, and then coordinates for the removable discontinuities and write the equations for the asymptotes. So, in number 1, f of x can be simplified by factoring the denominator, and a common factor of x can be factored out, which leaves us with a factor of x plus 1. And what we want to do now is to simplify that by canceling those common factors. So that's going to give us a simplified form of f of x equals 1 over x. But now we need to state explicitly the domain that was implied before, but now is no longer implied because we canceled common factors. Since we have a factor of x in the denominator, we know that x can't equal 0. Since we had a factor of x plus 1 in the denominator, we know that x can't equal negative 1. The x plus 1 was removed, so we must state that x may not equal negative 1. And that means that we have a removable discontinuity when x equals negative 1. I'll leave the y blank for now. There is an infinite discontinuity or a vertical asymptote when the denominator of the simplified form is equal to 0. So that means when x is equal to 0 and there's no addition or subtraction after the parent function y equals 1 over x. So that means that the horizontal asymptote for this graph is at y equals 0. Now let's go back to the removable discontinuity. Since our simplified form is 1 over x, we just need to substitute negative 1 into the simplified form to get a y value of negative 1. So there's a removable discontinuity at negative 1 comma negative 1. In number 2, this is a transformation of the parent function y equals 1 over x, and there are no common factors to remove here, or common factors to reduce the fraction. So we're going to leave the function as is, which means that there are no removable discontinuities. The denominator of the simplified form is equal to 0 when x is negative 5, so the vertical is x equals negative 5, and our translation up to tells us the horizontal asymptote must be at y equals 2. In number 3, h of x can be simplified by factoring 5 from the numerator and then canceling the common factors. So h of x simplifies to 5, but we've removed the discontinuity caused by the factor x minus 2 in the denominator. So we have to acknowledge that this is 4 values of x that are not equal to 2. That means we have a removable discontinuity when x is equal to 2. The y value for the removable discontinuity can be found by finding the y value in the simplified form. If h of x is always equal to 5, that means the y value is always 5, so the removable discontinuity has a y value of 5. This is a linear or constant function, a horizontal line, so that means there are no vertical asymptotes and no horizontal asymptotes. In number 4, we can simplify by factoring the denominator into x plus 3 times x minus 2. Since x minus 2 and 2 minus x are opposite factors, that means that f of x simplifies to negative 1 divided by x plus 3, but we have to acknowledge that we lost the factor of x minus 2 in the denominator, so we lost the discontinuity at x equals 2. So we can say that x is not equal to negative 2. That means we have a removable discontinuity when x is equal to 2. The y value will be equal to negative 1 divided by 2 plus 3. Just take f of x in simplified form and replace x with 2, and that will give us negative 1/5. So the y value here is negative 1/5. The vertical asymptote is found by setting our denominator of the simplified form equal to 0, so x is equal to negative 3, and the horizontal asymptote is y equals 0 because there is no addition or subtraction after the fractional form negative 1 over x plus 3. In number 5, there are no common factors to reduce this function g of x. So g of x's simplified form is just the same function. G of x is equal to negative 2 divided by x minus 3 minus 4. And that means that there are no removable discontinuities. The vertical asymptote is found by the value of x that makes the denominator equal to 0. So x equals 3. And the horizontal asymptote is found by the vertical translation of this graph, and so we see a minus 4 after the fractional value, so that means it's down 4, or the horizontal asymptote is at y equals negative 4. In 6, we have a little bit more factoring to do. Common factor of 2x upstairs, and that leaves us with 1 minus x squared, and downstairs we have x squared minus 1. We can factor a little bit more. 1 minus x squared is 1 plus x times 1 minus x, and x squared minus 1 is x plus 1 times x minus 1. Now 1 plus x and x plus 1 are the same factor, so they're going to cancel. But when we cancel the 1 minus x and the x minus 1, that's going to leave us with negative 1 because they are opposites. So our simplified form is h of x is equal to negative 2x, but we've removed both factors x plus 1 and x minus 1, so we have to acknowledge that x cannot equal either positive or negative 1. This indicates two removable discontinuities, one at negative 1 and one at positive 1. And I can find the y values by replacing x with negative 1 and also with x equals positive 1. When we replace x with negative 1, h of negative 1 is negative 2 times negative 1, which is positive 2. H of positive 1 is negative 2 times 1, which is negative 2. Since this is a linear function, there are no vertical asymptotes and no horizontal asymptotes. In number 7, there are no common factors to reduce, so f of x is just the same in simplified form, 1 over x plus 1 minus 3. That means there are no removable discontinuities. The vertical asymptote is the value of x at which the denominator is equal to 0, so that's x equals negative 1. Horizontal asymptote, y equals negative 3, since we see a translation down 3 in the parent function. So now we can find two extra points to graph here, one on each branch, by replacing x with two values and finding the y values. Now we want to pick values that are on either side of negative 1, so negative 2 and 0 would be ideal. When we replace x with negative 2, y is 1 over negative 2 plus 1 minus 3. That's equal to negative 1 minus 3, or negative 4. When x is 0, 1 over 0 plus 1 minus 3. That's 1 minus 3, or negative 2. Let's graph our asymptotes. We've got an asymptote at x equals negative 1. We've got another at y equals negative 3. And then we have one anchor point at negative 2 comma negative 4 and another at 0 comma negative 2. And then we know that this hyperbola approaches the horizontal and vertical asymptotes at both ends of each branch. For number 8, we can do some factoring. G of x is equal to x plus 2 over, and our denominator factors into x plus 2 times x minus 1. So that means in simplified form, g of x will equal 1 over x minus 1. And we're going to acknowledge the discontinuity that we removed, which is at x equals negative 2. And that means we have a removable discontinuity when x is equal to negative 2. I'm going to find the y value for this by replacing x with negative 2 in the function g of x. So that will give us negative 1/3. In our simplified form, the denominator is equal to 0 when x is equal to 1, so we have a vertical asymptote x equals 1. There is no vertical translation, so that means that the horizontal asymptote stays at y equals 0. I'm going to pick two values on either side of x equals 1, so 0 and 2, and replace x with those values in our simplified form. So 1 over 0 minus 1 is negative 1, and 1 over 2 minus 1 is positive 1. So let's graph our asymptotes. We've got x equals 1 and y equals 0. And then we have a branch with 0, negative 1, and a branch with 2, positive 1. Filling in the rest of this hyperbola, the graph will look like this. In number 9, there are no factors to cancel, so h of x is just equal to negative 2 divided by x minus 3. So that means there are no removable discontinuities. The denominator is equal to 0 when x is equal to 3, so vertical asymptote at x equals 3. There is no addition afterward. We can think of that as a plus 0, so that means our horizontal asymptote is equal to is y equals 0. Now we can find the points on each branch of the hyperbola by substituting in to the simplified version of h of x. And I'm going to pick values on either side of x equals 3. So one at 2 and one at 4. When x is 2, negative 2 over 2 minus 3 is positive 2. And when x is 4, negative 2 over 4 minus 3 is negative 2. Let's plot the asymptotes. X equals 3 and y equals 0. And then 1 point on each branch of this hyperbola. We have 2, 2, and we have 4, negative 2. And that kind of tells us where our branches are on the upper left of the two asymptotes intersection and the lower right of the intersections. Number 10 simplifies by factoring the numerator. The factors of the numerator are 2x minus 3 and x minus 1, so when we simplify we can remove the x minus 1 factors and f of x will be simplified to 2x minus 3. Having removed the x minus 1s, we have to acknowledge that x is not allowed to be equal to 1. That means we have a removable discontinuity at x equals 1. If we replace x with 1 in the simplified form, that means that we're going to find f of 1, basically, which is 2 times 1 minus 3. That's going to give us a negative 1 for the y value of the removable discontinuity. Since the resulting simplified form is a linear function, there is no vertical asymptote and there is no horizontal asymptote. When graphing the function, I'm just going to graph a function with a y-intercept of negative 3 and a slope of 2. But when I get to the point where x is equal to 1, I have to make sure that we have an open circle to indicate that there's a removable discontinuity or hole in the graph at that point. The function in number 11 has no common factors that allow for reducing, so g of x is just equal to 3 over x plus 1, which means there's no removable discontinuity. The vertical asymptote can be found by setting that denominator equal to 0, so x is equal to 0. Horizontal asymptote, we see the plus 1 outside of the reciprocal function, so that means translated up 1. Horizontal asymptote is y equals 1. I'm going to make a table of values using a point on either side of the vertical asymptote. So on either side of x equals 0, that would be negative 1 and positive 1. So 3 divided by negative 1 plus 1 is negative 3 plus 1, or negative 2. And 3 divided by positive 1 plus 1 is 4. So we're going to have a point at negative 1, negative 2, and one at 1, 4. And the vertical asymptote was x equals 0. So that's our vertical line. horizontal at y equals 1. And so that tells us what this hyperbola looks like, anchoring with each of those anchor points there. And the graph is approaching the vertical and horizontal asymptotes at either end of the branch. In number 12, we can simplify by factoring that denominator into x times x plus 1. That means our simplified form will be h of x is equal to 1 divided by x plus 1, but now we need to acknowledge that we lost the factor of x in the denominator, so x cannot equal 0. That means that we have a removable discontinuity when x is equal to 0. Take that simplified form and replace x with 0. 1 over 0 plus 1 is 1. So that gives us a 1 for the y-coordinate of the removable discontinuity. The vertical asymptote can be found by finding the value of x for which the denominator is equal to 0 in the simplified form. So x plus 1 equals 0 when x is equal to negative 1. And the horizontal asymptote is that vertical translation, so y is equal to 0. Now let's create a table of values for that simplified form. And our y value is 1 over x plus 1. I want to pick a value that's on either side of that vertical asymptote, x equals negative 1. So negative 2 and 0 would be good choices. 1 divided by negative 2 plus 1 is negative 1. 1 divided by 0 plus 1 is 1. So we'll have anchor points at negative 2 comma negative 1 and 0 comma 1. Horizontal asymptote is at y equals 0 and vertical asymptote is at x equals negative 1. That tells us what the two branches of the hyperbola look like. We're anchoring them in the upper right corner of the intersection of the two asymptotes and then the lower left. Number 13 has no common factors to reduce, so we already have the simplified form f of x equals 1 over x minus 2 minus 2. We have no removable discontinuity since I did not factor and cancel any common factors with the denominator. So our vertical asymptote is the value of x at which the denominator in the simplified form is equal to 0, so that's x equals 2. Horizontal asymptote, that vertical translation, so y is equal to negative 2. And let's take our simplified form and let's replace x with values on either side of x equals 2, so 1 and 3. 1 over 1 minus 2 is negative 1 minus 2 or negative 3. 1 over 3 minus 2 is 1 minus 2, which is negative 1. So we have anchor points at 1 comma negative 3 and 3 comma negative 1. We have a horizontal asymptote at y equals negative 2 and a vertical at x equals 2. And so that tells us what the hyperbola looks like with those anchor points graphed, sort of approaching the asymptotes on either side of the branch of each hyperbola, each branch of the hyperbola. Last exercise can definitely be simplified. A factor of x in the numerator and a factor of x in the denominator. The numerator can be factored further, x plus 1 times x minus 1. And that means both factors of x and x minus 1 can be canceled. So g of x is in simplified form x plus 1. But we need to acknowledge that we lost the factors of x and x minus 1. So x cannot equal 0, nor can x equal 1, which means we have removed those discontinuities. So we need to acknowledge those. Each discontinuity removable is at x equals 0 and at x equals 1. The y values are equal to x plus 1, so 0 plus 1 is 1, 1 plus 1 is 2. Since this function is a linear function, there are no vertical asymptotes, nor are there any horizontal asymptotes. We just have a y equals mx plus b. but we're going to have removable discontinuities at 0, 1 and at 1, 2. And this is would be a line that had it not had these restrictions, x can't equal 0 and x can't equal 1, would have just been a line with a y-intercept of 1 and a slope of 1. So now we can graph some additional points here for accuracy. And this will just be that line with those 2 points removed, so indicated with the holes in the graph.